Hey, Algebra 2, so we'll work through lesson 21. Now we're going to be graphing the natural logarithm function. If you remember, the natural logarithm is ln, and we are base e when we're a natural logarithm. Let's get into it. First of all, let's just do a little refresher. If I looked at these three graphs, what could we notice? That's a 3 about them. We have f of x equals log base 2 of x, g of x equals log base 3 of x, and h of x equals log of x, which I'm not writing it, but it's really base 10. Let's see, some similarities would be they're always increasing, where b is greater than 1. We can safely say they all cross the x-axis at x equals 1. Oops. Goodness. It's hard to draw very nicely on here. But they're all going to increase at different rates, either more rapidly or less rapidly, depending on the base. So these are all different bases. My handwriting is exceptional today, isn't it? Different bases. This should be similar. And they also all have the same domain and range. So our exploratory challenge, your task is to compare graphs of base b logarithm functions to the graph of the common logarithm function, f of x equals log x, and summarize your results. We don't have groups. Recall that the base of the common logarithm function is 10, and a graph of f is provided. So I'm going to go ahead and graph these and put a picture here for you. So I went ahead and graphed all of them, except I forgot to graph log base 10 of x. But we can tell that log base 10 would be right in between graphs 4 and 5, the purple and the orange, which would fall somewhere right in between there. Not quite in between, and a much nicer line than that. So I graphed them all, and there's the log base 10 of x. But that's on the previous page. It's okay. So let's talk about it. Describe how the graph of g for the base that you selected, which we did all, compares to the graph of f of x equals log base x. When the base was a fraction, the graph was a reflection over the x-axis. And then as the base got bigger, as the base increased, the graph increased slowly. It hugged the x-axis closer. D, share your results with your group. I went ahead and copied the answers in here so we can talk about all of them since we didn't have groups. When your base was a fraction, the function is decreasing. Its graph is a reflection about the horizontal axis. When your base is between 1 and 10, the graph appears to be a vertical scaling of log base 10 of x by a factor greater than 1. As the base gets closer to 10, the graph g gets closer to the graph of f and appears less steep. And then when we get much greater than 10, it's a vertical scaling by a factor between 0 and 1. So as the base grows, the graph of g grows at a slower rate and appears to move closer to the horizontal axis than the graphs of the logarithmic functions whose bases are closest to 10, right? So that's what you see if you go back and look at the graph, which, hey, I've got another one pictured here. Let's look at it. I forgot I did this. That's so funny. So as b gets greater and greater, our graph of the log base b gets closer and closer to the x-axis. It increases much slower. And then as b gets smaller, but not a fraction, still a whole number, it increases more rapidly. Cool. And then when your base is between 0 and 1, it's a reflection over the x-axis. So first of all, why are the functions decreasing when b is between 0 and 1? If we just look at it and we try to remember our log rules, I can change this into log of x over log of 1/2. So I'm dividing by a number. I can even mess with it a little bit more and say this is log 1 minus log 2. Log of 1 is 0, so that would be log of x over negative log 2. That's how it's a reflection. I've got that negative out there. And I'm dividing by a number, so it's going to get smaller, correct? So that sort of makes sense there. I can also put this into exponential form. One half to the what equals x. So if x is greater than 1, that means y is going to be less than 0. As x increases, y becomes larger in magnitude while staying negative, so therefore y actually decreases. So the function's decreasing, right? How does the graph of y equals log base b of x relate to the graph of y equals log base 1 over b, of x? How do those two relate to each other? Before we do that, let's just talk about how the exponential functions relate to each other. So if I have y equals b to the x and y equals 1 over b to the x, these are also reflections about an axis, but the vertical axis. Okay, if you remember, we've learned that one already. It's a reflection over the vertical axis because we know that 1 over b to the x equals b to the negative x. And that right there tells us a reflection over the vertical axis. So when we exchange the domain and range values by doing the inverses, they'll also be the reflections of one another, but about the horizontal axis. Okay, why do smaller bases, b is greater than 1, but still smaller bases, produce steeper graphs? And then, sorry, let's erase that. So why do bases greater than 1, but still small? My goodness. So b is greater than 1, but still small. Why do they produce steeper graphs? Where larger bases produce flatter graphs, graphs that hug the x-axis a little closer. So when we have a small base, they grow at a faster rate. making the graph steeper. For example, if I just looked at log base 2 of 64, that actually equals 6, because 2 raised to the 6th power is 64, where log base 4 of 64 equals 3, because 4 raised to the 3rd power is 64. Or I can even say log base 8 of 64 equals 2. The larger the base is, the slower it grows. So the same input of 64 produces a smaller output as the size of the base increases. Well, where would a natural log sit? Where would a natural log sit in this graph in relation to the graphs? We would say it's between the graphs of y equals log base 2 of x and y equals log base 5 of x, because e is between 2 and 5. And that's just using the graphs that we've graphed, that we've been working with to this point. I mean, obviously, it's actually between 2 and 3, but we didn't graph log base 3. So the graphs of these functions appear to be vertical scalings of each other, because we just proved it. We just graphed a bunch of them, right? So let's look at some exercises. So let's practice using the change base property to rewrite into common logarithms. If you remember, the change of base just says log base b of x equals, we're just changing them both to log 10, log of x over log of b. So they're both base 10. So very simply I can say this is equal to log of x over log of 1/4. Okay, log of x over log of 1/2. Same thing. Log of x over log of 2. Okay, we probably don't have to finish all of these. Log of x over log of 5. Log of x over log of 20. And log of x over log of 100, which we know log of 100, so we can say that's log of x over 2, because log of 100 is the number 2. So example 1, the graph of the natural logarithm function f of x equals log of x. Graph the natural logarithm function below to demonstrate where it sits in relation to the graphs of the base 2 and the base 10 logarithm functions. Sorry, I'm going to make that bigger. Our base 2 function is right here. And our base 10 function is right here. And awesomely enough, the natural log function goes right in between. It still crosses at x equals 1. I shouldn't have picked blue. So that's the same x-intercept. And let's see if I can give you any more notable spots. Not really. But that is where it sits in relation to base 2 and base 10. Graph each function by applying transformations of the graphs of the natural logarithm function. So here we have shift right, 1 unit, and there we have vertical transformation by a factor of 3. So let me get a little bit bigger pen here. So we know that, first let's just do, natural log of x there in red. I know I'm going to cross the x-axis right there, and that's 7 or 8. When I use a thicker pen, it looks a little bit better. And then we can do log of x minus 1 times 3. Since I'm shifting 1 to the right, my x-intercept is going to be at 2, and my vertical asymptote, which we haven't talked about much yet, changes from x equals 0 to x equals 1. And we're stretching by a factor of 3, so we're going to increase a little steeper. This asymptote thing just means that inside those parentheses, I can't be 0, nor can I be negative. So if I plugged in x equals 1, that would be a natural log of 0, which isn't possible. And if I plugged in anything less than 1, I would have natural log of a negative number, which isn't possible. So that vertical asymptote is just where we don't cross over as far as the x values go. It limits our domain, right? Okay, we're going to compare this to y equals natural log of x. So cross right there. Flattens out about like that. Now let's see how we can compare this. Get a pen out. We need to write this as a natural logarithm. So we have, excuse me, change our base formula, log x over log 6 minus 2. Not log 2, I'm so sorry. Log of x over log of 6 minus 2. Now I can do 1 over log 6 times log x minus 2, because 1 over log 6, 1 over natural log of 6 is about 0.558. So we know that how it's going to be vertically scaled, right? So this is my vertical scale factor. And then translate 2 down. See if I can do this. So I should cross right about there since I transferred 2 down. And it's actually going to be just a little bit flatter since my vertical scale is a number less than 1. That looks pretty good. If I look at Desmos, it should go up just a little bit more. Cool? And that's my last slide. Well, I hope that we talked a little bit more about asymptotes. When we shift our log function left or right, that moves the line that our graph can't cross. On this particular graph, our asymptote is at x equals 0. The previous one, what one was that? We shifted 1 to the right, so our asymptote was at x equals 1. And we're going to have a few more in our homework. So if you could check out the solutions and make sure you understand how the asymptotes work, right? All right, good job.